Hello, everybody. Welcome back. Welcome back. So, right now we're talking about measures of variability, and that is a box plot down there. Measures of variability. This is from chapter 5 of your Howell textbook. Remember, you can when you're looking at reading the chapter in here, you'll see other examples. There are some health examples, some interesting psychology examples in your textbook also. All right, and things explained just a little bit differently as well. Okay, measures of variability. So, our agenda today is to talk about what the general problem is. We'll talk about the range, we'll talk about deviation, we'll talk about variance, and then we'll visualize dispersion or visualize spread. So the general problem is that central tendency, which we talked about last time, only deals with what's in the center. And you don't get a sense of how spread out things are from that center. So if the average on students' math tests in an 11th grade class was 80, that's great, but you also don't know how spread out it is, right? So you don't know, say, how many kids scored below 60 and didn't do very well at all, you know. You just know where the center is. Okay, so some definitions. Now I am on slide 4. Dispersion or variability. Now, when I think of things dispersing, I think of, like, I don't know, people leaving an event and everybody disperses and goes home, right? And this is basically the same thing. Dispersion is the measure of how spread out folks are. So, or the variability. How spread out, or the variability, how much data points vary around some midpoint, usually the mean. And so the image in my mind is it's the baseball game has finished and people are leaving, and some people, you know, they left a little bit before the end, and they're real close to their car, and they've maybe started driving off, and then some people, you know, are just getting out of the stands. So how close or far away are people from the stadium? If we measured that, we'd be measuring the dispersion or the spread of folks. And in statistics, we're measuring the spread of data. It helps us convey more information about the data than just the central tendency. And so our first measure of dispersion or variability is the range. This is slide 5. It's the difference between the maximum and the minimum. So if the average on that math test was 80 and the scores ranged from 70 to 90, we know that the range was 20 points. Now the range can be influenced by extreme scores. So if you have that student who has had a lot of absences and they show up just in time for the test and they score 15 on the test, then you have your scores ranging from 15 to 90 and you'd have a really wide range of 75. Okay. Different samples of the population can have very different ranges, so that gives it a bit of instability, and it may not be the best estimate for a particular population because of these problems in terms of extreme scores and the variability, the instability, I should say. Okay, slide 6. Interquartile range. This is where you chop off the highest 25% and the lowest 25% of the scores, and the interquartile range is what remains. So those students who scored between the 75th percentile and the 25th percentile. So that middle group, okay, that were right around the mean. the middle 50% of your sample. So that kid who scored 15 because they haven't been in school all year and they just showed up in time for the test, they wouldn't be counted in the interquartile range. Okay, so that way you avoid that problem. So slide 7, the pros is it's not so influenced by extreme scores. The cons is it doesn't really tell us about how variable the sample is because we got rid of half of the sample. I mean, it does tell you like how close, half the class is to the mean, if that's what we're talking about. And it may estimate the central tendency better than the variability because the median is going to be right there in the middle. Okay. So, slide 8. When do we use the interquartile range? When we have extreme scores or a skewed distribution, it can be helpful. It doesn't use all the data, so you may want to report the full range along with it. Slide 9. A note about notation, okay? So here we're going to go back to our Greek, right? Our Greek, right? So different letters are used when we measure the whole population versus a sample. So for the mean, for a sample, we're going to use the letter M. You may have seen that used, or X bar, which we talked about last time. But for a population, we're going to use the Greek symbol mu. Okay? When we're talking about the mean of a population, we're using mu. Okay. And of course, N refers to the number of observed scores. And remember that language observed is from the history. Historically, experimenters would observe the rats doing something or whatever it was that they were observing. Okay. All right. Slide 10. Okay, deviation. And we're not talking about delinquents, deviants. We're talking about the distance between a score and the mean of the scores, okay? So the distance between a particular score and the arithmetic mean, the average, is the deviation, right? So if mu is the mean for the population, X would represent a particular person's value. So if I knew the average height of all women in the United States, I could take my height, subtract the average height, and know how far I deviate from the height of women in the United States. Now, if we could average all of these deviations, okay, we'd know how closely grouped or spread apart scores are, right? Because if scores are really close, like if that middle school math test where, was it 11th grade, where students scored 80, if a lot of kids scored 79, 78, 77, 76, 80 minus 79 is just 1. That's not a big deviation at all. 80 minus 76 is just 4. Again, not a big deviation. And if there were a bunch of kids on the other side, 81, 82, 83, 84, again, we would not get big deviations if they were in this kind of narrow range, right? And so, hey, if we took the average of all those deviations, then we could know how closely grouped or spread apart they were. Let's look at it. Let's talk about this a little bit more. So just some more notation. Deviation, the distance between a score and a measure of central tendency, usually the mean. So if we're talking about a population, a particular score minus mu. If we're talking about samples, it could be X minus X bar or X minus M might be how it would be written. Can we average the deviations? Let's try it. Let's look at slide 12. So we're trying to figure out this average deviation. And by the way, this is the lecture where some folks are like, oh yeah, I am in a statistics class. So if you're feeling like that, understandable. Okay, so we're trying to see if we can figure out this average deviation. If we combine what we're saying is how we calculate the deviation, or x minus mu, if we know the population average, and with the formula for taking the average, which is summation of all the x's divided by n, the total number in our sample, we can get the average deviation, right? We can sum x minus mu, or sum x minus mu, and divide it by n. Okay, slide 13. So let's try that. Let's say we gave a test to 3 students. They scored 45, 50, and 55 on that test. I'm on slide 13. What's the mean? Easy. Okay, the average of 45, 50, and 55 is 50. Now, what's the average deviation from the mean? If we did this in Excel, our first column would be calculations, right? Our next column is our variable. Our variable is score. We have 3 scores, 45, 50, and 55. Our next column is where we're putting the deviation. So 45, and our mean is 50, right? 45 minus 50 is negative 5. 50, our second student scored 50. 50 minus 50 is 0. And 55 minus 50 is 5. Okay, and so the next thing, the calculation we're going to make, we're going to sum for both columns. For the sum of the scores is 150. The sum of the deviations, though, minus 5 plus 0 plus 5 is 0. The minus 5 and the plus 5 cancel each other out. The average, then, you take the sum, you divide it by the total number of scores, or students, or whatever it is that you observed. The average score, 150 divided by 3 is 50. 0 divided by 3 is 0. Here's the thing. No matter what sample you have, your average of the deviations is always going to be 0. Why? Because the average is like the central value. And you're going to have the distance of the scores below your central value is going to be equal to the sum of the distances of the scores above your central value. That's why it's called an average, because it's in the center. So we can't really figure out what the average is if we're going to go through this process of actually doing the average the way we normally do. So, slide 14, can't use average deviation. It doesn't work. It always adds to 0. Somebody got the idea to square the deviations. Okay, now they no longer add to 0, and we can average them, right? Because we squared them. If you go back to slide 13, let's think about what the squared deviations would be. Okay, if the score is 45, and we're going to square that first deviation, negative 5, minus 10. If we do squaring is multiplying it by itself, right? So minus 5 times minus 5, and negative times a negative is a positive. 5 times 5 is 25. So we get our square deviation is 25. The square of 0 is still 0. The 5 squared is 5 times 5 is 25. The sum of that, okay, would be 25 plus 25. And then divided by 3. And it's not 0. Now we have 25 divided by 3. Not 0. Yay! We got away from that 0. What is it? 8 and a third, right? Okay. So that was but that would be our squared. So somebody got the idea to square the deviations. I have a feeling it was this guy named Carl Pearson back in the 1800s. Now they no longer add to 0. We can average them. And that's slide 14. Slide 15, the fancy name for the squared deviations that are then kind of like averaged by dividing by the total number of observations, or number of scores, or number of whatever it is that your data is comprised of, is called the variance. Okay, the variance. We square each deviation, then divide it by the total. Well, we square each deviation, then we sum all the deviations together, and then we divide it by the total. Because it's not an average if you're not adding something. Okay, so the population variance, we're going to use these Greek letters. It's going to be the lowercase sigma squared is the symbol. Wait, let me draw it this way for the video. Lowercase sigma squared is the symbol that means the population variance. Okay? And remember, we're trying to get a measure of how wide apart the data is spread around the mean. Okay? And we use this formula if we measure every individual in the population, which we almost never do in education, or psychology, or sports, because we usually have a sample. Okay, so variance. Now there's a formula modification that's going to have to be made if we're taking a sample. Because if we're taking a sample, the calculation is biased. The reason is we used the numbers in our sample to calculate our mean. So we used the numbers in our sample to calculate X bar if we don't already know what mu is, or the population mean. And so to correct that bias, and now I'm going to slide 17, instead of dividing by the number, we have to divide by the number minus 1. Okay, and it's related to something called degrees of freedom, which sounds like it's a political thing, but it's actually not in statistics. If you were using a sample, you have the deviation, right? Your score minus the mean score. You square that. You add up all those squared deviations. You divide it by n minus 1. That's how you get the variance. Okay, for a sample, which is usually what you'll be doing. Is you usually be getting the variance for a sample. And slide 18. So we usually don't talk about the variance very much, but standard deviation is something we do talk about quite frequently out in the real world. It's the square root of the variance. And the reason we want to take the square root is we want to get back to the original units. Where is my phone? So, I don't know if I can do, my real calculator's at school. I don't know if I can do square root on my phone calculator. I'm going to have to get a good calculator app for my phone. But it gets us back to the original units. So that we're not dealing in squared land. We're back to whatever our original measure was, whether it was the years, like when we were talking about figuring out the average year that folks in this class were born, or whether it's scores on a test. It's a measure of how far scores deviate from the mean in the same units as your original measure, and Carl Pearson, I was right, in the late 1800s, Carl Pearson devised the standard deviation. Okay, so now how do we visualize this? Slide 17. Visualizing dispersion. Okay, so we know one way, histograms. Slide 19 is visualizing dispersion, title slide, and slide 20, a histogram, is one way, right? We know. So scores on a middle school test at one school, the mean is 80, most of the scores. The standard deviation is, if you look at the printout really closely, is 10.075, which rounds to 10.1 points. Most of the scores will fall then within plus or minus 1 standard deviation, which is 10.1 points. But it would be hard to compare this histogram to histograms from other schools. And so if you're a leader, often you're making comparisons among relatively large groups of data. So you're comparing one class to another, or one school to another, that kind of thing. A particular school to the state averages, that kind of thing. But it's kind of hard to compare histograms. So there's a thing called box plots, and we mentioned this when we were talking about displaying data. But now we can really talk about it because you know more. So a box plot is a display that shows the center and the variability, and it allows the comparison of multiple distributions. It also draws attention to outliers, and it can help you screen your data for errors because there may be some crazy scores in there that shouldn't be there, and that probably meant that someone typed something in wrong. Okay, so slide 22. To calculate you kind of draw a box plot. The calculation steps you need in order to draw your box plot are you need to know what the median is. That's your 50th percentile point, and that's where the first line goes. And then you find your top and bottom 25th percentile, so that's your quartiles. So you draw a line at the 75th percentile and a line at the 25th percentile. Now, don't feel like you have to scribble all this down or really remember it, because frankly, we're going to get the computer to do this drawing for us. And then you multiply the interquartile range. Remember, the interquartile range is from 25 to 75. You multiply that interquartile range by 1.5 and add subtract from the quartiles to draw the fences or the tops of the whiskers, and any remaining points are outliers. It's much easier to look at an example. Slide 23. Here's an example. In 1991, there was a general social survey that the federal government did. Now, if they wanted to show that they, got the same ages around race, across different races of respondents to fill out this survey, then they can use a box plot to show that, right? And so, pardon me, I got some dinner stuck in my teeth. Sorry about that. So looking at this box plot along the x-axis, we have three groups. So that's categorical data. We have the race of the respondent. Sometimes people who answer surveys are called respondents. They're categorized as white, black, or other. Along the y-axis, we have age of respondent ranging, and the axis ranges from 0 to 110. A 110-year-old would be a pretty senior person to respond to a survey. Okay, if you look at the lines, let's look for the white respondents. The line in the middle of the box, right? That's our median. Okay, so at around the 50th percentile, the person was the median is a little bit higher than 40 for white respondents. It's right around 40 for black respondents, and it's a little below 40 for other. And you can see if the size of the boxes gives you a sense of the range. And the boxes, even though the white box is the largest and then the others are a little bit smaller, they are pretty similar in terms of where most of the ages of the respondents or the middle 50% fell. Now, then you get the whiskers, right? So it's sometimes called a box and whisker plot, where at the top, you see those lines at the top, okay? And at the bottom, those are 1.5 times the interquartile range. So you can see that the data tended to spread out upward, right? Because you're not really going to be able to survey, a 10-year-old, right? And so the data kind of spreads out where you get up to like an 80-year-old responding to, is that a 9? No, yeah, it's by, 60, 60, 78, that's a 90, up to 90. up to 90-year-olds responding to the survey. I had to adjust my laptop there. Okay, so that gives you a sense of box plots that were similar. Now let's look at slide 24. This example is from a paper that I just submitted with Dr. DeYoung. And the title of the paper is The Impact of Curricular Coaches on Teacher Retention. We were interested in whether the presence of a curricular coach, like a literacy coach or a math coach, mattered for elementary school teachers, and whether they stayed at their school, whether they transferred to another school, or whether they quit the profession altogether. And we were looking at new teachers, so teachers who were in their first, second, or third year of teaching, right? And because it's those new teachers that tend to be most likely to quit. And so we wanted to see, okay, what are some things at schools that can reduce turnover? And here's what we found. Along the x-axis, you see we have 6 groups. The first 2 groups of teachers are those who are in their first year of teaching. The second 2 groups are those teachers who are in their second year of teaching. And the last 2 groups of teachers are those who are in their third year of teaching. And then among those years, we divided the teachers between those teachers where there was no curricular coach at their school. There was no literacy coach. There was no math coach. Or sometimes it's called literacy specialist or math specialist or teacher on special assignment, that kind of thing. And those where there was a coach. Same thing for second year and third year. We're comparing those teachers who had no coach at their school versus teachers where they're new elementary school teachers where there was one or more coaches at their school. And then along the y-axis, it says fitted probability of leaving versus staying. So we were looking at basically the probability that the teachers quit. And by leaving, we mean leave the profession, like they quit teaching altogether. Okay, and you see that that ranges from 0% probability up to 0.60 on that axis. And 0.60 is a 60%, right? Probability. Remember that proportion percent thing with the M&Ms? Okay, so the line in the middle of the box, that's your median probability of quitting the profession if you're a new elementary school teacher. And this was national data, so we were looking at teachers across the United States. And you can see that first year teachers, their boxes are a little higher than the other teachers. That means they have a slightly higher probability of leaving the profession. And you see that the higher box for first year teachers is for those first year teachers who had no coach at their school. And that means they had the highest probability of leaving the profession as compared to teachers who stayed. Okay, or the highest risk is another way you could say it. And then so on the box, you see there's the box, and then there are the whiskers, and then there are all those dots above. Those represent outliers. Okay, so people who didn't fall within 1.5 times the interquartile range. And so there's a lot of variability. So you can tell it's pretty spread out upward in terms of higher probabilities of leaving, because you can't really go below a 0 probability of leaving, but you can go higher than a 0.1 or 10% probability of leaving. So you see there's quite a bit of spread, and that's most likely due to other factors at the school. And so you can see that when you compare no coach to coach for any of the years, the probability of leaving is lower where there's a coach. All right. So something to think about for those of you who are principals and district leaders and looking at how to improve retention of early career elementary school teachers. Okay. Slide 25. When do we use these measures? So this is our summary slide. We're going to use the range and the interquartile range and report it alongside the median when we have ordinal data, so categorical data that's ordinal. When we have interval and ratio data, so continuous data with or without a zero, meaningful zero, especially when the data is skewed. When you've got that skewed continuous data, your median and your range can be really helpful to give the reader an idea of what the typical values were. Variance and standard deviation, you're going to report that alongside the mean. Now, the vast majority of time, we're talking about the reporting the mean, reporting the standard deviation. It's practically standard to report the mean and the standard deviation. The variance is the standard deviation squared, right? So usually you don't talk about unless it relates to a specific procedure, and I'll be showing you when you're going to be talking about the variance. So interval and ratio data, that's continuous data with or without a meaningful zero, particularly when that data is symmetrical and unimodal. Now, in practice, people report the mean and the standard deviation regardless of how symmetrical the data is or unimodal. But in terms of best practice, if you really want your reader or listener to understand where your middle value is and kind of how dispersed the values were, or your scores or your data was, then when you've got skewed data, do talk about the median and the interquartile range, even though you'll probably also report the mean and standard deviation. Okay, that's all for now. This will be much clearer when I show you an example. Okay, have a good night.